Now let us continue our discussion to the derivative of transcendental functions. And as you can see right from here, the definition of a function that is transcendental is that it is not an algebraic function and that it includes functions like trigonometric, inverse trigonometric, logarithmic, exponential, and its analogs like the hyperbolic and inverse hyperbolic. So when we say transcendental functions again, they are those functions that actually transcend the rules of algebra. So you can just use the rules that we have used before in dealing with these kind of functions. For example, the René Descartes rule of sign in finding the possible composition or the possible combination of the roots of a certain function. So you can't apply that in transcendental functions because they're not actually polynomial functions. And we have 6, so we'll be dealing with all of them in today's video. And the first one would be the derivative of trigonometric functions. And I believe I've discussed all of these before, since I needed to give you an idea of how trig functions work for us to finalize the discussion for our preliminary until semifinals. So again, the derivatives are if it's sine, then we have cosine u, and then don't forget to differentiate the function that is we're taking the sine of that function. So that's u, and then we have du over dx. And then for cosine, we have negative sine, tangent secant squared, cotangent negative cosecant squared, secant secant u tangent, and then for the cosecant, we have negative cosecant and then cotangent. Now before I give examples from this kind of functions, let me just finish all the transcendental functions first, and I want you to memorize each rule or each derivative because you'll be using that when we evaluate examples from this. So the next one is the derivative of inverse trigonometric functions. So to find x from this expression, you take the inverse of that expression, then we can read this as x equals arc sine of u. Now there are 6 inverse functions, inverse trigonometric functions. So we have the derivative of the inverse of sine u, that's 1 over the square root of 1 minus u squared, of course the derivative of u. So this means that you have to take the square of what's inside and then subtract it from 1 and then make sure that it's on the denominator. And then the same way for our inverse cosine, it's just that it looks like the sine derivative, it's just that you have negative 1 at the numerator. So that's negative 1 divided by square root of 1 minus u squared. And then for the tangent, it's like you differentiate this in a sense that you put 1 plus u squared at the denominator instead of having the square root of 1 minus something. So that's the tip for tangent. And now I wanted to give a shortcut for this, knowing that it's tangent and it's kind of like t, which if you want to translate that in mathematical expression, that's positive or plus. So the easiest way to remember this is that there is a plus at the denominator, and then of course it's always u squared for these inverse trigonometric functions. So you add 1 plus u squared in that case. That's making it easier to remember this derivative. Now you proceed with cosecant inverse of u. Now remember, when you're differentiating functions or trigonometric functions that starts with co, the resulting answer to that would always be negative. Like this one, that's cosecant inverse of u, or the arc cosecant of u. So the derivative is not the inverse of, it's not the reciprocal of this derivative of sine, but there's a different rule for that. So we have negative 1 over u and then square root of u squared minus 1. Now you can actually redefine this by placing u inside the radical sign, so that makes it u squared times u squared minus 1. But it is always best to have this form because later in the expression you would understand that all you have to do is to express that in the simplest form possible. And just remember, when we're dealing with the cosecant, inverse and then secant inverse, you should remember that the property is that the function itself, or the u itself, is kind of greater than 1. So you should be having something like it should be the one that 1 is being subtracted from. So that's u squared, unlike this sign, which is 1 minus u squared. So it's like the opposite, or should I say, you interchange the two denominators. So that's u squared minus 1, and then for secant squared, secant inverse of u, so we have 1 over u and then square root of u squared minus 1, and then for cotangent inverse, it's just the negative of the tangent inverse derivative. So that's it for our inverse trigonometric function, and I want you to memorize this with the trigonometric functions, because later on we'll be using this. So if you do, then you may now proceed with the next transcendental function, which is the logarithmic functions, and of course exponential. Now before we start, let me just give some short or quick discussions about logarithmic functions, because I believe that this is very important before we start differentiating. So logarithmic functions, as we all know, is a function wherein it is expressed in x is equal to log of y base a. So it comes from the function, or the exponential function, y equals a to the x. So a is always a positive number, that should be noted. And then in a similar way, we could see that a raised to log of x base a, that's equal to x, and then log of a to the x base a is equal to x. So this is one of the properties of logarithmic functions. And these functions are only defined when x is greater than 0, and of course that's an infinity. Now, just to give you an idea, if we're taking the logarithmic of a 0 value, then we won't be able to get an answer for that, because that's how logarithmic function works. They don't actually have any value for 0, so they have this asymptote at x is equal to 0. And then of course you cannot substitute infinity to such kind of expression. So thing is, the x value should be something like defined. Okay. Now let's have these 8 properties. These are the basic properties of logarithm, and as you can see here, I'll be explaining some of these using an example. So the first one is that the log of n is equal to log of m plus log of n. So this simply means that if I have, for example, the logarithm of 12, I can actually express this in terms of log of 4, and then I add log of logarithm of 3. So this can be expressed in this way, because if you have 4 times 3, that's 12, so that's m times n. Now, when I talk about this logarithm, there are actually 2 types of this, and this is actually described at this portion. When I say log, just log of 12 without any base, I'm talking about the common logarithms known as the Briggshian logarithm. So this is basically log base 10. However, for other cases, we have the natural logarithm, also called the Naperian logarithm, which is, of course, these are more commonly used, and it's denoted by ln of that certain number. So this is basically log of the number base e. So that's the e is the Euler's constant. So basically we'll be using both of them, but most of the time I'll be using, I think, Naperian, because that's the easiest one. Alright, so for the next one, we have log of m raised to n. So the thing is, what happens in this property is that you can actually take the exponent and put it in front of that log, meaning it is multiplied. So for example, I have log of 8. I can actually express this in terms of log of 2 cubed, which makes this also equal to 8. And then I can also express it in terms of 3 times the logarithm of 2. That's base 10. Okay, so that's it for the second property. Now for the third, we have log of m over n, and it says here that you can actually take the difference between these two, the numerator being the first one and then the denominator being the second. So with this, if I have, for example, log of 12 again, and we know that this 12 can actually be expressed in terms of, let's say, log of 24 over 2. So I can now express this in terms of log of 24 minus log of 2. And in that way, you'll be able to get the same answer from this. Okay. And then for the next one, number 4, we have log of m raised to 1 over n. That is simply equal to 1 over n times log of m. And this is actually a complement to the second rule. It's just that you multiply this with the logarithm of m. You take out the exponent, then you put it in front of the logarithm expression. So that's just like multiplying. So 2 and 4, they're just like the same property. Now let's head on to rule number 5. Now this is a very important expression, one of the most basic expressions that you have to remember, because whenever you see something like b and then you have a base that's the same with your expression, that's always equal to 1. It's like because this is the base, for example, you want to express it in terms of an exponential function. So if you have b and then you need to find this exponent, and actually in exponential function, this is what is the exponent right here. And then you need to find a value that is equal to b. Then what could probably be the answer for this? So you know very well that that's 1, because that's what makes this expression the same. So whenever you see something like a value wherein, for example, you have log of let's say x plus 8, and even though this is x plus 8, but the base is still x plus 8, this is equal to 1 still, even if the base is kind of complicated. But if it's the same as the one that we're taking the logarithm of, then it would just be equal to 1. Let's head on to this problem. If we would be taking that certain kind of idea that we used to do when we want to express this in terms of exponential function, we know that we just have to take the base and then raise this to whatever is that equivalent of this logarithm. So if we raise that to 0, then we know very well that this is equal to 1. And this is the expression why this number 6 is equivalent to 0. Because if you take the logarithm of 1 into base b, then that is equal to 0. Now let's head on to this log of m base b. And this is a very easy expression to remember. You just have to like dissect this expression into two. Something like you take the log of m and then divide that with the log of the base. So for an example, if you have, let's say, log of let's have the logarithm of, let's say, 35, and then we have a base 4. So this is actually equal to the logarithm of 35, and then you divide that by the logarithm of 4. So you would just get the same answer for this. And this is very helpful when you're trying to differentiate things when it gets really kind of complicated. Now for this final expression, as you can see right from here, we're actually taking the reciprocal of the logarithm, wherein we interchange the base and then the one that we're taking the logarithm of. And this is true because remember, this expression, we can actually use rule number 7 to evaluate this. For example, this is actually equal to log of b over log of m. And basically what happens that since this is actually the reciprocal, this goes to the numerator and then this left the denominator. So that's log of m over log of b. Okay, so that is this one is actually the same as this number 7. So that's the properties that we're actually toying with. They are actually quite connected with each other, and basically if you remember all of these, and then if you just take a good memorize, or if you just take a good look and memorize all of these, and then you won't have any problem with differentiating logarithmic functions. And by the way, even though you don't, or you're not quite familiar with all of the rules, it's something like it's not really that important if you know all of these, or I mean you're an expert in logarithm. It's just that if you can differentiate or apply properties of logarithm, then you can actually find the value or the answer without even memorizing things. It's just that this helps in simplifying the expressions. So if you don't have, if you memorize the rules for logarithmic functions, but you're not kind of able to simplify it, then the problem lies in this area wherein you're not actually quite versed in the properties of logarithmic functions. But anyway, so let's move on to those that uses this Napier logarithm, and these are actually the analogs of these properties. They are just also derived from this. So as you can see here, it just follow the same pattern. So if you want to, for example, use the e value instead of having something like u, so we have log of e, which is the Euler's constant. So that's basically log of e, and then of base a over ln of, log of a. So for the first rule, if we try to apply the rule 8 or 7, so basically what happens is that we take something like 1 over the log of a base e, and we know that log of e translates to the natural logarithm. So that makes perfect sense for this one, because this expression actually translates this to ln of a. Now for this one, you just have to apply the seventh rule. So that is having ln of u and then ln of a. So the reason for that is that why is it that you can actually use logarithm and then you can actually use ln? So the reason for that is that you're actually dividing them. So even if you're trying to use a different base by taking the logarithm of that value, it will just cancel out because you're actually dividing. So the base doesn't actually matter in this case. You can actually try that. For example, if I have, let's say, the log of 8 base 5, and then for some reason you were you had an idea wherein instead of using a base 10, you use, for example, log of 8 base 6, and then you try to have something like log of 5 then base 6. You will still get the same answer because you're actually dividing these two, and even if they have different bases, something like an arbitrary base we're setting, you will just get the same answer because that's a division property that it is ruled out in this process. So that's the same for taking ln. So if you're finding difficulty in expressing that in logarithm, you can just use the ln. And then it's the same way if you want to express this ln of u in terms of the logarithm. So that's just taking u. And we know very well that this is ln, so the base here is e, so that's log of e. And then this number 4 is just a complement to rule number 1 and rule number 8. Okay, so for example, we have here, so we have log of 7 of x is equal to log of x. Actually, these are examples that are already been solved. So if we want to take this one, we can express that using our rule number 7. So we have the log of x and then log of 7. And that is also equal to 1 over the log of x is 7 because that's stated in our rule number 8. So that's like interchanging our expression. Now if we have this number 2, so how do we express this log of zy of base ab? So you just apply rule number 7. So remember, this also can be expressed in terms of ln of zy and then ln of ab. It's just the same thing. And then of course this is zy, so based on our property number one, this is the product inside that logarithm expression. So you can actually use plus, separate them the two in two terms. Separate the term in two terms, and then just use h1 of the expression. So that's z. Actually, this should be plus log of y. Okay, not m. Where did I get that m? Anyway, so that's the expression. And then for number 3, that's a b ln of e raised a plus b. That's equal to this one. But how do we prove this? So we know quite well that if we have ln of e raised to a plus b, we can actually do something like multiply this with or bring this down so that it multiplies with our expression. So that's a plus b, and then we're left with ln of e. And we know very well that ln of e is actually 1. So we're left with ab and then a plus b. So it's also a very good example wherein we could apply these rules here as well as those that are stated here. Now, there's a note here, and I would also like to emphasize this. We're not actually differentiating. We're just applying the properties so that we can prepare for the logarithmic expression that we might be dealing with in this problem. Okay, so it's also said here that when you're lacking your skills in logarithm, you might as well want to browse over your books in your previous school years, because I believe that this is discussed in high school, or if it's not, then junior or senior high. So you might want to review them so that you would have a good grasp of what happens when we talk about logarithm. Now, knowing all of those expressions that we need to remember, now we proceed with the derivative of logarithmic functions, and it says here that we only have two. So if you have the logarithm of u with base a, that's actually taking the log of e base a over u, or you can express that in terms of 1 over u and then the ln of a. So again, this ln of a came from rule number 8, because this log of e base a, we can actually express that in terms of log of e over log of a. And then instead of expressing this in terms of this expression, we can actually use 1 and then over this log of a over log of e, and then this is actually equal to 1 over ln of a. Okay, so if I were you, I would just choose this 1 over u ln of a, because I believe that this is the easiest logarithm expression that you can actually use. But of course, if you're finding it hard, then use this for the direct application of the properties. But anyway, so we proceed with number 2. So the derivative of ln u is just the reciprocal of u, and then you take the derivative of the function itself. So that's it for our logarithmic functions. So the difference between this 1 and 2 is that you can see here that they have both this 1 over u, that's something like the reciprocal of our function. But in this expression for the first one, because we have the logarithm and with the base a, so it's actually using this 1 over ln of a, or the natural logarithm of a, instead of just having this 1. Because basically, if we take this expression, that's actually taking the ln of e, which becomes just positive 1. Now let's move on with the derivative of exponential functions. And the first one is that if we have a to the u, this is actually equal to a to the u and then ln a. This is the easiest expression that we can remember. But if you want to be a martyr of this calculus, you can actually use this expression, because that's just the same property. Remember, this log of a over log of e is just the same as ln of a. And then for number 2, if we have the Euler's constant being raised to a certain number, that's just the number itself. Now, I don't know if you've seen this meme, but a wild Pokemon e to the x appear, and then something like your only choice is to like differentiate and then integrate. So it's not very effective if you try to differentiate and then integrate e to the x, because you know that it will just result to the same answer. So the thing is, even if it's e to the x, or I mean, let's say this one is e to the x squared. So don't forget to, like, if you copy this e to the x squared, don't forget to differentiate the exponent, because that's actually included in the rule. In any rule that we talk about, u should be differentiated, because all transcendental functions are like do the basic rule and then we add or multiply with this chain rule that we need. And I'm talking about this derivative of u as the chain rule that we are actually doing. And I know you're quite familiar with this when you're dealing with trigonometric functions, because they are actually like automatic chain rule that we do, because whenever you have u or any value of x, you would always like to differentiate of the value that's inside that trigonometric expression. It's just that we're always dealing with x or 2x, something like those. So the derivative is kind of easy to do, but when it comes to the semifinals, it will get a little complicated. So don't forget to differentiate those u functions inside these transcendental functions. And now I think this is the most complicated one for all exponential functions. That is, if we have u to the v. So u to the v is something like you have two independent variables being they are expressed in exponential functions. So, for example, you have x raised to 3x. This is one of the examples that I can give you. So, it says here that the derivative is something like v raised to u times v minus 1. So, if you would look at this expression, you can see that this looks something like the power rule. And if you would be looking at this one or this one, it looks like this is the the exponential rule that we use in logarithm. Actually, this is number 1 rule in exponential functions. So, for cases like this, when you have an independent variable raised to an independent variable, all you have to do is to remember that this is a combination of the power rule and then the exponential rule. Let's use this one. So if I'll be doing this, then I can just say that if this is power rule, I'll be treating this first as a constant. So if I'll be treating this as a constant, then the derivative should be something like you multiply this with our exponent and then x, then raise this to the exponent, then subtract it by 1. And then it says here that you need to take the derivative of u with respect to x. And our u here is the base. So in this case, the base is x, so you multiply this with 1. And we're done with the first term. Now for the second one, it says here that we need to copy u to the v, or the expression itself. So we copy it, x to the 3x, and then we take the ln of that expression. So we take the ln of that expression. Okay, so that's fairly easy one to do. And then you take the derivative of the exponent, and the derivative of the exponent is actually 3. So therefore, if we would try to simplify this expression by taking this or writing this, you can actually have something like 3, let's say 3x times x raised to 3x minus 1, and then that is added with 3 3 to the x, and then ln of x raised to 3x. Okay, so this is the answer for that expression if you want to take the derivative of that. So it looks kind of complicated at first, but when you get a good understanding of how this works, it's actually very easy. And there is another way that we can solve for this, but I want to save that for the next video we're trying to do all the differentiation consecutively. Do a lot of items with respect to transcendental functions. So now let's move on to the last, which is the hyperbolic functions. Now, hyperbolic functions are those that are analogs of trigonometric functions. And as you can see here from the figure, this is what the hyperbolic functions look like. So the red one is the graph of the tangent, the sine, hyperbolic sine of x. So if you have, let's say for example, this is your hyperbola, this is one of those openings, it opens upward. So if you would just take the one opening of that hyperbola, that's actually the expression of hyperbolic cosine of x, and sine is the one that goes from the right side and then it crosses the origin or the symmetry and then it goes down. That's the hyperbolic sine. And then the tangent, of course, is the one that is intercepted by this hyperbolic sine of x. So it's like it's trying to like draw a line that is kind of perpendicular with our hyperbolic sine of x. So that's just how this looks like in a hyperbola graph. And now, knowing all of this, there are actually ways that we can read this hyperbolic sine, cosine, tangent. Some books read this as sine x. This one is cos x. Some read this as tan x, and the others are just a hyperbolic cotangent, secant, hyperbolic, or even secant h. They read these expressions like those things. But in this case, I would like to read this as if it's sine h of x or even hyperbolic sine of x, because I want to emphasize that it's hyperbolic. Okay, that's just the only reason why. I don't know. I don't actually get comfortable reading it as sine or cosine. But of course, it's all up to you. It's all up to the person reading it. Let's have the properties of these hyperbolic functions, and you can see it from here, the properties. I will not be elaborating much into this. It's just an expression of the Euler's constant with the values of x. So for example, if we have sine h of 2z, so that's actually our u here, or x here, is the 2z itself. So now if we'll be applying this rule, we just have to copy e and then raise that to the x, and x here is actually 2z. So you follow this rule, and then that's e to the 2z, and then minus e raised to negative 2z all over 2. Now how about tangent h of 3? So 3 is a constant right here, and if you look at x, we can see here that it's e raised to x minus e raised to negative x. So you just have to follow this expression. So we have it right here, and then it will give you a value at your a value. Now for our cosine h of ln of x, so you have this cosine of h, so that's e raised to x, and then remember this e raised to x, and then this is your x, and then if we would be simplifying this e raised to ln of x, that's actually e raised log of x base e. And remember in our previous discussion about logarithm or exponential functions, this is actually simplified to 1, so that leaves this value as x. So that's x, and then remember this is not actually something like negative x. You don't do that, but that's actually something like e raised to ln of x raised to negative 1, because that's the property wherein we can actually bring this down. So that's what is applied here. That's why x raised to negative 1 is left in this expression. And remember, we're not yet differentiating. We're actually just taking a look at the properties and how it is applied in certain conditions where we have this mix of logarithm and then hyperbolic functions. Now lastly, we have this ln of cosecant hyperbolic of x. So that is equal to ln of this expression, and that is perfectly true, because if you would be looking at this cosecant of hx, that's actually the same expression. So you just have to take the ln of that, and then by virtue of the rule number 3, I think, in logarithmic functions, so we can actually do this. We separate them by subtraction, so we're left with this expression, and then you can actually simplify this expression in terms of e to the x minus 1 over e raised to x, and that's why we're left with this expression. So that's just this, and then by the virtue of, again, of using this rule number 3, wherein we can separate this and then subtract this with the expression, we're left with something like this at the final value. Actually, this can be rewritten. I will be giving you the dissected part. So that's ln of e raised to 2x minus 1, and then that should be minus ln of e raised to x. And knowing that this is ln of e raised to x, this turns out to be just x, but this one is negative, so that becomes positive x, and this one becomes negative. So that's what happens when we try to evaluate this. And sometimes I need to I would require you to give the simplified form, so you might as well want to memorize this, because it gives you an upper hand in dealing with these mixed problems. Okay, so this is the graph, and then this is the properties of hyperbolic functions. You might as well want to memorize this. These are the analogs of these trigonometric functions. So if it is positive in the trigonometric functions, remember in hyperbolic that's negative, and you start with cosine. So the idea here is that you start with the one that is alphabetically first, something like that, because if you compare cosine and sine, the one that comes first would be cosine, because that's letter C. So that's the mnemonics for that. You'll be writing cosine first, and then you subtract, because the opposite is positive to make it 1 in trigonometric function. And then you just memorize all of this, and then it'll just be easy for you. Now we try to differentiate these hyperbolic functions. So we do have this sine h of u, that's cosine of h of u, and then for cosine we have sine h, tangent h, we have secant h squared. And then unlike our trigonometric functions when we differentiate something like functions that has a co-functions, the values or the derivatives are actually negative. But in this case, it's not applicable, because in hyperbolic functions, the values that are, the derivatives that are negative are actually the reciprocal functions. When I say reciprocal functions, those are the reciprocal functions of the three main trigonometric functions that we have, and these are the sine, cosine, and then tangent. So if you take the reciprocal of that, we have let's say secant, and then cosecant, and then cotangent. So those three in hyperbolic functions, when you try to differentiate them, you will always get a negative answer for that. And it's just the same concept for trigonometric functions. It's just that you add h on those expressions, and of course the different signs that you might be needing when dealing with those values. And then the last one is that this the derivative of inverse hyperbolic functions. And now because these functions, remember, it has an equivalent value, so if you try to take the inverse of this, we would have to expect that the inverse of that would be having this logarithm, because we have an exponential function for that. And this is actually those the expressions when we try to take the inverse of each of the hyperbolic functions. So you might as well want to memorize all of this. Okay, but if you're finding it difficult to memorize, then you can just derive it from these expressions. It will just be the same thing. Anyway, but I would recommend you to memorize this. And then for the derivatives, we have here the inverse of sine. That's actually 1 over square root of u squared plus 1. And then for cosine of h inverse, that's u squared minus 1. And then the difference between these two from our trigonometric functions, that as you can see from there, 1 comes first before u in sine and cosine, but in this case u comes first before 1. And that's it. That's the difference from the trigonometric function. And then for tangent h, instead of plus, we have minus. And then for the cotangent secant and then cosecant h, we actually have for the inverse cotangent h, this actually this expression is mathematically the same as number 3 if you'd be evaluating this. But we stick with this rule. If you see cotangent h and then that's derivative, you directly differentiate that in terms of this rule. And then for the secant h, it's just it looks the same for our secant and cosecant in trigonometry, but the only difference is that 1 comes first before u, because in trigo, again, u comes first before 1. So that's our those are the points that we need to remember when we try to memorize all of these rules, because the only thing that you can do before you start differentiating is to memorize all of these rules, because you can't actually differentiate when you haven't memorized all of this. So before we differentiate properly using these identities, using these transcendental functions, I want you to memorize all of these rules first, so that you won't really get confused when I try to do multiple things, especially when the composition of functions are mixed of any of these transcendental functions. Okay, so there's a module assessment right here. So if you already understood the previous topics, the approximation and differentials, you can actually try this. But I'll be dealing with the derivative of the functions in our next video. Okay, so see you then.